Hello everyone, welcome back to Mr. Lee's Math Class Videos. I'm Mr. Lee. We're picking up in 7.5. We've introduced the inverse or arc trig functions. So really number 2 is 3 more examples that are similar to what we did on the last problem. So I'll leave you those to practice. And sometimes we can use calculators to find these if they're not nice angles that work out to good trig values. So for example, the only 3 buttons that will be on your calculator are going to be a sine inverse, a cosine inverse, and a tangent inverse. So if you end up with like a secant inverse, sometimes you have to figure your way through it. Mainly speaking, that we know that secant and cosine are reciprocals, but they have reciprocal values. In the case, if you look through this, secant inverse of x equals y, you can take the secant of both sides to cancel out the secant inverse. So x is the secant of y, which becomes 1 over cosine y. And if you move the cosine y to the left and the x to the right by multiplying and dividing, you'll get the cosine y as 1 over x. So y is the cosine inverse of 1 over x. And if both of these things are equal to y, then they are equal to each other. So when you are flipping for, say, secant, cosecant, or cotangent, you take 1 over the angle on the inside. You do not take 1 over on the outsides. So when you are doing this, secant inverse of 5.93, and there's no secant inverse button on your calculator, this is the cosine inverse, because they're reciprocals, of 1 over 5.93. Now because this asks for it in degrees, make sure if you're putting this in the calculator, you are in degrees. And then you'll find, depending on what kind of calculator you have, the cosine, what looks like to the negative first power, and then you can put that 1 over 5.93 in to get 80.29 degrees. Your calculator will already know there's only one specific value, so it already knows what quadrants it could possibly be in. Again, cotangent, I want you to try this one. This should be the tangent inverse of 1 over 0.418. So keep that in mind. It wants it in radians, so make sure to switch your mode as needed. Now this brings us to what I would consider the most fun part, at least for me, of the inverse trig functions, is when you have double trig functions. These involve drawing triangles, and we'll see this. You draw a triangle for the inner function, label your sides and your theta, or your angle, replace the inner function with theta, and then take the outer trig function of that angle. So it's easier to show how it works in a problem. For example, if you have the sine of the tangent inverse of 3/2, you use the inside to find this. You say theta is equal to the tangent inverse of 3/2. What that really means is that the tangent of theta is 3/2 if you take the tangent of both sides. We know tangent of theta is opposite over adjacent. And using the Pythagorean theorem, 3 squared is 9, 2 squared is 4, 9 plus 4 is 13. That tells you that the other side of this triangle is square root of 13. But the tangent inverse of 3/2, that takes the ratio and spits out the angle. That gives you the theta, because it will take these ratios and spit out this angle. But that takes the problem to being, really, I just need the sine of theta, because this produces an angle from the ratios. And once I've drawn the triangle, I can take the sine of that angle to go back to a ratio. So this converted a ratio to an angle, and this one will then convert the angle back to the ratio, and then you draw the picture to develop it. Now sine of theta is opposite over hypotenuse, so 3 over root 13, or 3 square roots of 13 over 13. So let's do one more just to see how this works. And it can have an arc on the inside or not. And I can leave one for you to do. The tangent of the arc cosine of 3/4 I'll leave for you to do because it's positive. I want to show how the negatives work. So the sine inverse of -1/5, we know that sine is negative only in connecting to the first quadrant in the fourth quadrant. So we can draw the triangle here. We have theta. Sine is opposite over hypotenuse, so -1 over 5. The hypotenuse will never be negative. The good news about this is that we're never in the third quadrant when we do the inverse trig functions, which means the negative will always go to the side you see, and the third side you are finding will always be positive. Now 5 squared is 25. Negative 1 squared is 1. 25 minus 1 is 24. So this is really the square root of 24, or 2 square roots of 6. So we have theta equals the sine inverse of negative 1/5. This helped us produce the triangle, but that turns our equation into the secant of theta because these two things are equal. And once I have the triangle, I can take the secant of theta. We know cosine is adjacent over hypotenuse. That means secant is hypotenuse over adjacent. This is 5 over 2 square roots of 6, or 5 square roots of 6 over 12. Again, I'll leave 4 for you to do. Now, you might think that's about as bad as they possibly get. It's not, because you have your double angle identities and you have your sum and difference identities, so you can start applying those. In the case of double angle identities, it still works the same. You're still going to be theta equals whatever the inverse trig function is, the tangent inverse of 12/5. That will help you produce your triangle. It's positive, so it's in the first quadrant. Theta opposite 12 over adjacent 5. Using Pythagorean theorem, 5, 12, it's a 5, 12, 13 triangle. That takes your equation to the sine of 2 theta, just on this. However, using your identities, sine of 2 theta is equal to 2 sine theta cosine theta. So we don't have a triangle for 2 theta, so it won't help us. But we do know that double angles can be broken down into their components. And from there, all we would need is the sine and the cosine for this. This is 2 sine of theta, 12 over 13. Cosine of theta, 5 over 13. Multiply them all together. This is 60 times 2, 120 over 169. The rules are still the same here. It has to be between -1 and 1, but it's taking skills you've already used and seeing how it works with the new ones we're developing. This works for a plus b as well. Here's a. So I'm going to call this, they're both positive, so this is a triangle for a. This is b. So I'm going to call this angle A, and angle A, the triangle is sine is 3/5, which leads the other side to be 4. Here's angle B. It's a second triangle whose cosine is 5/13, leaves 12. So we really have A is equal to the sine inverse of 3/5. B is equal to the cosine inverse of 5/13. So this is the cosine of now replacing them with the angle, because again, the inverse trig functions produce the angle of A plus B. And we know that this is cosine A, cosine B, minus sine A, sine B. Cosine of A, adjacent over hypotenuse, 4/5. Cosine B, adjacent over hypotenuse, 5/13. Sine of A, 3/5. And you'll notice the sine of A should match the inverse sine here. Similarly, the cosine of B matched the cosine inverse of angle B. Sine of B was 12/13. And when you put them together, you'll get 20 over 65 minus 36 over 65, which is -16/65. So you can see that these interact very easily with the other types of trig identities that we've learned, the sums and differences, the double angle identities, but these are really how they behave, and this is all for 7.5.